So say you're taking your part three exam and you get a question similar to this, where you see that dose, and I think it's important also to notice here that this X is signified by this. What are the four categories of dose that algorithms must consider? Describe terma. What is a convolution? How do you describe kernel and what kinds are there? What is superposition? How does this equation account for heterogeneities? What are the rules for photon and electron algorithms in terms of modeling fluence and accuracy? This is kind of more like little tidbits I wanted to throw in there, and I didn't really know how to do it. So first of all, the categories. So we have our primary dose. We also have our phantom scatter. And so this also is considered the patient. Any phantom, anything that's incident, the beam's incident on. We have contaminant charged particles. And then we have the head scatter dose. So those are the four categories that we have to consider, the dose algorithms have to consider when determining and correctly assessing and estimating dose. So what is terma? Simply, this is just total energy released in matter. This symbol is a convolution. So dose is equal to the terma convolved with the kernel. So what is this convolution? What is that? What's that mean then? So convolution is an operation, a mathematical operation that shows the overlap between two functions. We use it when we want to use a constant kernel that doesn't vary with density. So that's important because when you just do a convolution, this means that there is no heterogeneity correction. So if you just have homogeneous dose, this is great. You can convolve and you're ready to rock and roll, but that's a limitation of it. So what's a kernel and what kinds are there? So kernels spread out terma over an area, and these are Monte Carlo pre-calculated. They are essentially the dose deposition of the secondary electrons that are set in motion by those primary interactions. So we have pencil kernels, we have point kernels, and so depending on the accuracy and how long you want the calculation to take, that will depend whether you want a pencil or point. So what is superposition now? So we know what convolution is. So a superposition is similar to convolution, but it uses density to scale the kernel prior to convolution, and therefore we can account for heterogeneities inside a model. This is what is meant, or this means that it is spatially dependent and patient dependent. So that is important because, again, convolution, there's no heterogeneity correction. However, when you use superposition, it uses the density, it scales this kernel here, and that allows us to consider patients and phantoms individually. It makes it patient dependent, and it also makes it dependent on where that beam interacts within a phantom. So it's spatially dependent, it's patient dependent, and you have a heterogeneity in correction that's going to make it much more accurate, and that is what we use in our clinic. So we do superposition convolution in our clinic and for our dose algorithms. So how can that account for heterogeneities? Essentially, just the kernel can be scaled based on the density of the material. And then what just are some general little rules? So photon calculations work better at low energies, and they are very good at modeling primary fluence, but they do have to approximate the secondary interactions. Electron calculations have to model all of the secondary interactions. And so ultimately anything that's more accurate means that it's going to be slower because it has to simulate more secondary particles. So that in general is dose algorithms, a very quick run through, but I think this at bare minimum is what you need to know for part three. Definitely feel free to jump in Khan or any other reference of your choice to dive deeper and better understand the algorithms. And best of luck studying. If you have comments, please post them below.